right. I want to talk about differentials. Differentials is a slightly way to look at a derivative, and it's going to come really useful when we get to second quarter of college calculus, when you start to look at integrals or antiderivatives. But let's start by talking about some definitions. First of all, given a function y equals f of x, we know that the derivative of y with respect to x can be written as f prime of x. Two different notations, but they are equivalent, so we can write them as equal to each other. So let's think about what these things mean. Dx is some infinitesimal change in y, infinitesimal change in x. I said y there for a second, but and dy is the resulting change in y. And if we think about these, that means that we could, in that context, is this infinitesimal change, we can calculate the change in y by taking the derivative and multiplying it by the change in x. So one of the things we do have to notice here is that this is a dependent variable because it depends on both x and dx. So I could tell you that x is equal to 1, and I'm interested in a change right there, but I also have to tell you that I'm going to go 0.01 to the right for you to calculate the change in y. So that might be going up or down, but it might be doing something different going off to the left. All right, let's look at some examples of how we use this. So example 5, we've got some function y equals x to the 5th plus 37x. And what I want to know is at x equals 1, for a change in x of 0.01, how does y change? So what do I know? Well, I know that I can write that dy is equal to 5x to the 4th plus 37 times dx. The derivative of y with respect to x, f prime of x, and the infinitesimal change in x, which means that the change in y will equal 5 times 1 to the 4th plus 37 multiplied by 0.01, which is 0.42. The interpretation of that is that at x equals 1, if I increase x by 0.01, y will increase by 0.42. That is the definition of a differential, and that's how we use it. So let's do a couple more examples just to get us used to this. Let's look at the function y equals sine of 3x. I want to know what's happening at x equals pi, and I want to know what happens if I reduce my value of x by 0.02. So dy is equal to 3 cosine of 3x dx. And I'm not going to go through the individual how to find the derivatives. I'm going to assume that at this point you're pretty comfortable with that. So this means that the change in y is equal to 3 times the cosine of 3 pi times negative 0.02. I know the cosine of 3 pi is negative 1, and multiplying this all together, I get 0.06. At x equals pi, if I decrease x by 0.02, y will increase by 0.06. Again, remember, at a particular point, if I do some small change in X, I can calculate what my change in Y is going to be. Okay, let's do one more example. And the example I want to do now, I could just solve this for Y, but I'm not going to. I'm going to use implicit differentiation just to show you that it can be done. And the question is, at X equals 2, if I increase X by 0.05, what happens to Y? And let's look at this with the implicit differentiation. Well, first of all, I'm taking the derivative of the left and the derivative of the right. The sum rule says that this would be the derivative of X plus the derivative of Y. The product rule says that this is derivative of X times Y plus the derivative of Y times X. Collecting my dy's on one side, collecting my dx's on the other side, I get dy minus x dy equals y dx minus dx. This gives me 1 minus x dy is equal to y minus 1 dx, which means that the change in y would be y minus 1 over 1 minus x times that change in x. So I know that x is 2. I am going to have to calculate y here because I don't know y. I was only given an x. So I know that 2 plus y equals 2 times y, which means that y must equal 2. And so now I know that the change in y is equal to 2 minus 1 divided by 1 minus 2 times 0.05, which is negative 0.05. So again, an interpretation at x equals 2. If I increase x by 0.05, then y will decrease by 0.05. All right. So one other topic that's related to this is called sensitivity, and I'm actually not going to spend much time on sensitivity, but the question for sensitivity is, given some infinitesimal change in x, is the change in y big or small? If it's big, then y is sensitive to changes in x. And if it's small, then y is insensitive to changes in x. And this is useful because you want to have a basic idea of what a reaction is going to be. For example, if a patient is on a particular drug and the drug changes body temperature. Let's say 1 milligram of drug changes temp by, I'm just making up numbers here, by 3 degrees. What does 1.1 milligrams do? A sensitive reaction would mean that a change, a dx of 0.1, would give us a large temperature increase, which means we need to be very careful with our dosages. An insensitive relationship would say that a change of 0.1 in the drug dosage doesn't really change the temperature at all, which means that we don't need to worry too much about how close to 1 milligram our drug doses actually are. So there's an example of sensitivity. Again, we're not going to really talk about this much more, but I did want you to at least see it And now for those of you in my class, why don't you go ahead and do exercise 15 in the book, which is some calculations of dy. And we'll come back with the next video. I'm going to do an extra video on this section or this section of the book on Newton's method. And we'll come back and we'll tag that on. All right. Thanks for watching.